Okay, so we have been discussing where are neuromorphic cameras really good for. You heard special applications from Andre. We are still suffering in structure from motion applications. And then there has been, of course, action recognition. But are we really doing better? Most actions that we have in the computer vision community are really based on static classification. You see the objects and you know already what's going on. And our classic video cameras are very good at that. So, okay, what we have been looking at is now some actions where really the motion matters. So, and why would this be good? In situations of human-robot collaboration, where really milliseconds work to close and shorten the delay in the control loop between perception and actions. And we looked at actions. We recorded this a while ago in Telluride and now processed it, where people grabbed an object and then did different things on it. So here you see the famous Professor Andreas picking up the stone and either scribbling with it, playing with it, drawing with it, different actions with the stone. And so we did with other objects, spatulas, glasses. And we processed, a paper has been out already where we processed this on RGB videos a while ago. And now we compared with the newest architectures, event vision against video. And guess what? Here really event vision matters. So you can get the intuition already here in these actions, for example, actions with a spoon or actions with a cup. Event vision doesn't see the object before the hand doesn't come in contact with it. And video features, as you will see, actually get very confused because those video features pick up a lot of stuff. They pick up the texture and so on. So the architectures we have trained from the literature. There's a recurrent neural network, a GRU network that receives as input time surfaces. So the thing that Riyad has been talking about, slices of time surfaces, or a 3D convolution where we put them, the whole block. Those architectures have to see the whole block. So it's standards, but we compare. So in the one case you get them individually, in the other case you get them as a whole block. And then of course now a transformer architecture here, a mobile net transformer architecture that's very efficient, which also receives time surfaces and then builds the whole attention models. First, just a check, how does it compare to other architectures? This on the famous DVS gesture set, about comparable, the efficient GRU beats on this data set. And now let us look at this event architecture. So here, as you get the event visualized here over 2 seconds, in this sequence, so we assume we're only looking at the actions on the same object. Yeah. So after about a quarter of a second, you have a low confidence. After 1 second, the action gets already up to 44.9. And after 2 seconds, what's ending here, you have already a confidence of 92.8%. When you compare this to video, it's much lower, 28.5%. Only because it gets confused by other things. And here at the end of the action, what's usually done in computer vision, we're still quite here in this, it's still quite ahead, the event vision, as opposed to the action vision. So if you compare it, there was a whole data set on multiple objects compared. on videos you do much better if you say categorize all the knife actions, all the cup actions, all the stone actions. You have lots of confusion on the events. But assuming that we know it is that objects, event vision really can pull out the motion features. The work which has been done in Francisco Barranco's group with his student, it also includes a tracker which showed some advantages in efficiency but not real advantages in performance. So event vision really has some advantages on actions where motion matters. That's the conclusion. Thank you.